Good morning. Hope you're all doing great. So today we shall continue our discussion on arrays, and we will see a few interesting programs on arrays, and also take up this topic of time complexity of programs uh, and try to understand it in a simplistic way. Starting from Monday class, we will start with functions. And after that, we will look at pointers. So by the end of next class, pretty much all the important features of C programming language, they are available. So you already know, you would be knowing by the end of next week. As it is at this point itself, you are empowered. You can do most interesting problems with whatever the language constructs that are introduced in this course so far. In the next week, by the end of next week, you will be completely be on the top of the things. And so after that, it's all, we try to look at problems of different, which require different kinds of computational thinking, etc. And also language features also. There are other interesting language features which are essential when you are trying to build complex programs. I would like to revisit this simple program where we are reading a sequence of 10 numbers or n numbers. Here n turned out to be 10 from keyboard or from a file. We read it from the file through redirection. And on line in the loop, in the for loops, starting from line 17 to line 20, in general, the code starting from line 16 to line 20, we are computing the sum of elements in the array. If you see, we are iterating through this loop for n times. We are iterating through this loop n times. So the amount of work that we are doing, amount of work done, amount of work that we are doing in this loop is proportional to n. We are iterating through this loop n times, and in the loop there is only one statement, which is an addition operation. Similarly, if you see this loop from line 24 to line 29, so we are iterating through this loop n times, and in the loop we are doing one comparison operation and one assignment operation, but you are doing some constant amount of work within the loop. So here you are doing constant amount of work. When I say constant amount of work, that means that work is independent of the size of the overall input, that is n numbers. So in the loop here, we are doing constant amount of work. Here also within this loop, we are doing constant amount of work, and we are iterating through this loop n number of times. So the amount of work done is proportional to n. So keep this idea in mind, because we will be revisiting this idea again. Just want to highlight this. So this is a constant amount of work. Within the loop. So here also it's a constant amount of work, but it could be a different constant, but that's all right. This idea about time complexity of algorithms, programs, etc., you will study in detail in your data structures and algorithms course, and again in your algorithms course. So we will not get into very much detail here. you will not get into very much detail here. But I want to give you some intuition uh, which for you, so that you can reason about programs at some level. And the total amount of work that is done in this program, if you see, so here in order to read input, you are doing some amount of work. So here also it is proportional to n. So the total amount of work that is done, so it consists of it is n plus n plus n. This n corresponds to reading the input, and let's say the second n corresponds to computing the sum of the numbers in the array, and the third n corresponds to uh, computing the maximum of the array. Now let's look at using two-dimensional arrays. We have already seen two-dimensional arrays in the last class. So here is a program to initialize an identity matrix, because identity matrix would be useful in many matrix computations. So we are writing a program to initialize an identity matrix. And all we are, so in the loop, so you can see the declaration here on line 7, we are declaring an array named A. It has 2 dimensions. And the number of elements in each dimension is n. So it's a 4 by 4 array. Yeah, so just think of scanf as constant amount of work. Like for example, when we are reading an array, we iterate, we read each element of an array. Let's say you consume constant. So scanf takes, let's say it's a constant amount of work. So in order to read n elements of an array, you do work proportional to n. It would be better to what are the questions that we have? It's better that they are relevant to what we are discussing right now. So any other discussion, you can take it offline, if it's all right. So on line number 9 to line number 13, so what we are doing is we are initializing we are initializing the whole matrix to 0. So so this is what is called as an outer loop. So we have an outer loop. Within that outer loop, you have an inner loop. So in this loop, so we iterate through the elements of the array. So let's say if this is your array, so the way we are iterating is we fix using the outer loop. Let's say we fix I is equal to 0, and then we say j is equal to 0 to n. It goes, in this case, n is 4, or it goes actually 0 to 3. So what happens is you go in the inner loop. What happens is you go, j goes from 0 to 3, and you initialize the first row of the array. And then again you go back to the outer loop, you make I is equal to 1, and then again you use the inner loop to iterate through the elements in the row indexed 1, and you initialize them to 0. You do the same for second and third rows also. After that is done, so in this loop here, you have only one loop, and what we are doing is here we are we are making a of 0, 0 equal to 1, a of 1, comma 1 equal to 1, so on and so forth. And so that's all. And in line 19 to line 24, we are just printing this array. So there are some nice ideas on better ways of initializing an identity matrix. So I am with you. So there are definitely better ways of initializing the matrix. Let's first see this program though. GCC identity.c. So this is a way to initialize. It becomes so we have initialized a identity matrix and we have printed it. So before we go, the amount of work that we do in this program, if you see in this loop, we are doing work proportional to n square. We are iterating through this statement on line 11. It is visited n square. We are doing work proportional to n square. So here we are doing work proportional to n, and here we are doing work proportional to n square. So the total amount of work that we are doing is, if you add them together, it is n square plus n plus n square. So you can see the work that is being done on line 11 and line 16 and on line 21, they may take slightly different amount of, it could be, it's constant amount of work. The constant could be different, but roughly we say it's constant amount of work. Right? So now there are few suggestions on how we can improve this code. So it's all good. So let's see. So one suggestion is let's see. Okay. Anyway, so one suggestion that is given there is this. So one suggestion is, so here in this loop, what we can do is, if I equal to j, then so what we, if I is not equal to j, if I is not equal to j, we initialize it this way. Otherwise, we initialize it by saying a of ij is equal to 1. This is one idea. So there is this question on control backslash. Thank you, Shub. I didn't know that command. Next time I will use it. So constant amount of work means you can do, the amount of work that you are doing is independent of the value of n, where like if whether n is equal to 4 or 10 or 20 or 30, the amount of work that you are doing on line 12 is constant. But better way to think about it is you are just iterating through this loop, the statements from 11 to 14, that if statement, it is being encountered n square times. So now in this, if you look at this, I'm not exactly qualifying this constant amount of work, but approximately what I want to say is, it is independent of n. So if you see the amount of work that is done using these two loops, the outer loop and inner loop, is it is proportional to n square. Now, if else does some work, so that's why it is, let's say, if then else does k amount of work, then the actual work could be something like k n square. So instead of saying k n square, we are saying work is proportional to n square. Are you with me on this one? So the amount of work that is being done. So if you want to be exact, which is actually difficult, but you can say work is equal to k n square, and this k depends upon what is present inside the loop. Okay, if you have an if statement, k could be something. If instead of having an if statement, if you just have a of ij is equal to 0, that k could be something else. But in terms of proportionality, we can say the work is proportional to n squared. That's what it is. If you understand this much, then you are good. There is an alternate mechanism also some of you proposed. That is, you can maybe say this is equal to 0, and that is we are initializing the whole array. Control backslash. Awesome. Thank you. So we can comment. So yeah, we initialize the whole of the array A to 0, and then we have code from line 19 to 21 to initialize just a diagonal matrix. This also works. Let's see if this works. I'm curious. I think it should work. Yeah, it's working. Great. So now let's look at one more program. Line 14 to 11 to 14. If we had some So the question is, let's say if it is something like, yeah, okay, let's go to the next program and see. I'll try to answer that question. Yeah, initializing the matrix also does work proportional to n squared. Just because it is done in a different way doesn't mean that work is not there. Yeah, you're right, Gaurav. Well, you can make it global, but we'll take it up later, Kishore. It causes a bit of confusion. But there are, I'll answer your question later, Kishore, because it's not that easy. So you may. Now let's come to this program where we are trying to compute the sum of two matrices. So from line 11 to line 14, we are reading a matrix. We are reading a 2 by 2 matrix. From line 19 to line 23, we are reading a 2 by 2 matrix. From line 25 to 29, we are computing the sum of the two matrices. So here again, if you see, the amount of work that is being done, if you want exactly calculate, let's say in order to do this computation, you do k amount of work, and you are invoking this computation n square times. So you can say the amount of work done by this whole loop starting from 25 to 29 is k n square, but we don't want to, let's not bother about those constants, and we can say the work done is proportional to n square approximately. As I said, I'm trying to give you some intuition. Later on in your data structures course, algorithms course, we'll study it in detail. I think this should answer one of the questions that is being asked earlier. So just to do the work done on line 27, it may take k, it's k amount of work. And since we are invoking that work k n square times, the total work is k n square. But we can kind of ignore that constant and say, no, the work done is proportional to n square. Are you with me in this algorithm? This algorithm is pretty simple. We are just iterating through the entries of the two matrices. Now we are computing the sum of the product. Each element, if you see, essentially what we are doing is, this is matrix A, this is matrix B. You want to add them together and to get matrix C. So what we are doing is we are iterating through the elements of this matrix C, one row after another. And in general, if you think of this element as the element Cij, you know the element Cij is equal to Aij plus Bij, and that's what we are doing. That is how we are computing the sum of the two matrices. Great. So I think you're all with me so far. So let's try this out. GCC, why is there %6D? I just want to, you should tell, you did all the homeworks, na? And you should tell why there is %6D. In order, I just want to print the matrix prettily, that's all. There is no other. Does the 2D array takes input in a row measure method or a column measure method? It's a wrong question to ask, Kush, actually. So here, the matrix, just want to make it clear since you brought it up, the matrix, if you take a 2 by 2 matrix, A, so the elements of the matrix are A00, A01, A10, A11. We have seen this in the last class. The way it is, so this matrix is laid out in the memory in this particular form. So A00 is present here, A01 is present here, A10 is present here, A11 is present here. This mapping of this matrix to this memory, this is a in the row measure form. But how do you read the elements of this matrix? It's completely up to you. Like for example, in this particular example, we are reading this matrix in first this entry, after this entry, after this entry, after this entry. But then it is possible for you to read, like for example, you can use an alternate way. You can first read this entry, followed by that you can read this, and then like you can go back and then read this, and then you can come here and read this. So it's up to us to see how you want to read it. It's a programming logic. Like for example, in order for us to be able to read this in this particular form, all you have to do is, if you say here I'm reading this, if I make like this, then what happens is something happened. So if you see now, if you focus here on line 13, what is happening is so you are fixing I is equal to 0. And you are iterating through j. J is the row index. So that means you end up reading the matrix A one column at a time. So how you read it is completely up to us. No. Please, Kush, you have to understand the memory layout is fixed. A of the way this matrix is mapped to memory is exactly the same. It's not going to change anything. It's not going to change anything. It is actually possible for you to read the entries of this matrix in an arbitrary random order. This matrix is, no, not at all. It doesn't depend at all on the way we read the matrix. The matrix, the way this matrix is mapped to the memory, it is fixed. It's not going to change. This mapping is fixed. Whether you want to read the elements of this matrix column wise or row wise, it's all up to you on how you write your code. Good. So now let's go to matrix multiplication problem. So matrix multiplication. So again, see here what we are doing is this is matrix multiplication. Yeah, this is matrix multiplication. So actually, we didn't run this code, GCC matrix sum.c. So let's check this code. 1, 2, 2, 3, matrix B, -1, -2. Let's say I'll say 0, 0. Then you can see the sum of the two matrices is this. Okay. So now let's move on to matrix multiplication. In the matrix multiplication problem, so let me share the white board. So in the matrix multiplication problem, let's say you have this is matrix A and this is matrix B. Let's, for the sake of simplicity, we can think of it as two square matrices. Although it really doesn't matter. So like for example, this can be n by m and this can be m by o. Okay, so okay, so let's reduce the number of suffixes. They unnecessarily confuse. So let's take these are all two n by n matrices. The product is also an n by n matrix. And you know that from your no, from your intermediate mathematics that if you want to compute the element C00 of the product matrix, you take the 0th row here and you take the 0th column here and you take the dot product of it. And so essentially, if you see, so C00 is equal to A00 times B00 plus, so that is you take the element here and you take the element here, you multiply, and then you take the element here and then you take the element here. So the index increases A01 and it will be B10 because we are sticking to column 0 here. And similarly, you after that you go to A02 and then you come here, it is B so B to 0, so on and so forth. So in general, you can write it like this. This is equal to, so k going to 1 to n, A0 k2 B k0. Because you want to iterate through the elements of the row 0 of matrix A and iterate through elements of the column 0 of the matrix B, and you want to uh, compute a dot product likewise. So in general, if you want to compute, if you look at the element Cij here, you took the ith column, ith row here, you took the ith row, this is ith row, this is row I, and then you take the column j. So you take column j and then you compute the dot product of row I and column j. Just want to see if there are any questions here. Okay, not any critical questions per se, so I think I can go ahead. So in general, if you want to compute the element Cij, you want to take the dot product of the ith row and the jth column of ith row of matrix A and jth column of matrix B, and this is nothing but sigma k is equal to 1 to n Ci k, sorry, not Cik, Aik into Bkj. This is how you compute the dot element Cij here. Are you all with me here on how we compute the I comma jth element of the product matrix? You have to take the ith row of the matrix A and jth column of matrix B. You want to take the dot product of it. I want to see if you're all doing all right so far. This is standard the matrix multiplication that you see in your intermediate. Yeah, it is aik times bj. So here you have to go through, you pick the ith row of matrix A, and if you look at elements in the ith row of the matrix A, so this index I remains the same, but what changes is the index k. All the elements in the ith row of matrix A, their first index will be I. It's not going to change. The row index is going to be the same, but the column index keeps changing. And if you look at all the elements in the jth column of matrix B, the column index remains the same, but what keeps changing is the row index. So we want to take this element and this element, and when we take this element and this element, this is k is equal to 0. Yeah, so this should be, sorry. Yeah, I think I got this one wrong. This should be 0 to n minus 1. Sorry. And so after this, we go to the next element here and the next element here. Let me use a different color to say we pair this element and we pair this element. And what is this? This is B1J. This is AI1. So we pair this element with this element and we multiply with each other. And if you want to see, like for example, after that, we may have AI2 here, and then here you have B2J. So we pair this yellow element with the yellow element here, and we multiply it together. And this is what we do. So if you're all with me here, which is again, it's intermediate mathematics, we can just go ahead and try to see the program for it. So given this, so before I go, so given this computational procedure, so do you think you will be able to write code for matrix multiplication? Some of you may have already done, but just want to check if you're all with me here. Great. So now let's look at, so let's look at the matrix multiplication code. In the matrix multiplication code, so from line 11 to line 17, we are reading matrix A. And from line 19 to line 27, we are reading matrix B. And on line 29 to line 38, we are computing the product of the two matrices. And on line 42 to line 49, we are printing the computed product matrix. I just want you to focus on line 29 to line 28. So what we are doing is we are iterating through what we are looking for is, so we have the product matrix C. So what we are doing is this. Okay, so what we are doing is we are iterating. This is product matrix C. We are computing the elements of the product matrix first one row at a time. First we compute the elements of the 0th row, and so when we say I is equal to 0, so this outer loop says that we are computing the elements of the ith row of the product matrix. Are you seeing the screen, or yeah, you should be able to see? You are able to see the code, right? Okay, great. So when I is equal to 0, whatever the value of I which the outer iteration sets, then we are working on row I. And here on line 31 in the inner loop, what the inner loop is doing is it is trying to, so here when whatever, so we fix on row I, based on which row we fix on depends upon the value which the outer loop iteration variable I takes. You go to row I, and then you iterate through the elements of this row one at a time. And so here in this loop, we are actually computing the, let's say when I is equal to some value and j is equal to some value. Let's say this is Cij, this is Cij. Then what we are doing is we just, you know that Cij is nothing but sigma I is equal to 0 to n minus 1 aik times bkj. And that's what we are exactly doing here. So we are initializing this sum to 0, and we are iterating through different products here, and we are accumulating them in the sum. And after we accumulate in the sum on line number 26, we assign it to the variable Cij. So there are few questions there. Before I answer those questions, are you all with me on this logic? The innermost loop is uh, to compute the the value Cij, the innermost loop. So here, now it is important. Earlier, I said, let's say when you are printing the matrix, the amount of work that is being done is proportional to n square. And we think that the work that is being done on line 46 is constant. But if you see the work that is being done from line number 33 to 36, it is not constant because it is dependent on n. So you are doing n amount of work within this 2D loop. So you are visiting this 2D loop n square times, and in order to compute each element of the product matrix, you are doing n amount of work. So it is no longer constant. It's very, very important. It's to realize this fact, this observation, that the amount of work done to compute, in the case of matrix sum, the amount of work done to compute the element Cij is constant. But the amount of work done to compute element Cij while computing the product, it is not constant, it is proportional to n. So here in this particular case, we can say approximately the work done in this is proportional to n cube, because so you visit the statement, for example, line 35, approximately n cube times. So we say the work done is proportional to n cube. So you can do more accurate counting of amount of work done. Like, but because, for example, if you see line 36, some of you may have this question. If you see line 36, the number of times statement 36 gets invoked is proportional to n square. Let's say the amount of work done with respect to uh, line 36 is k1 n square, okay, and this is k2 n square. No, this is k2 n cube. This is k2 n cube, and this is also k3 n square. So you may say the total amount of work done is like k1 n square plus k2 n cube plus k3 n square. So you can kind of do a more accurate calculation of work done, but later on towards, so in this class itself, I will justify why you can kind of approximate the total work done as proportional to n cube. Are you with me here on this particular thing, that line 33, it is k3 n square, and line 35 k2 n cube, line 36 k1 n square, total amount of work done. We add them up, and which part you didn't get, Gaurav? See, the amount of this is when you translate it in terms of the work done. So here you are just doing a copy operation to some variable, and here you are doing multiplication and addition. Here again you are doing copy operation to an array element. So approximately it's like, like these are different kinds of tasks, and each of the tasks may take different amount of time. And so that is where we are using K1, K2, K, because we are, let's say, the amount of work that is required, K1 is the amount of work we have to do this assignment. And we are doing this assignment statement n square times. So we say total amount of work done with respect to this statement is K1 n square. Similarly, let's say the amount of work done to execute line 35 is K2. And we are invoking this for n cube number of times. So it is K2 n cube is the total time taken. And similarly, if you see this one, let's assume K3 is amount of work done to initialize sum is equal to 0. And again, we are initializing sum is equal to 0 n square times. So the total amount of work done with respect to statement 33 is K3 n square. So if you add these things up, this is K1 n square plus K2 n cube plus K3 n square. No, n cube is not for one row of the n cube. Within, when we execute this whole loop, it will, the code from 29 to 38, if you see it just, so if after the execution, the product matrix is available. I didn't get questions from Gaurav. Why will the total loop request K1 n square? Okay. Yeah, that's true. End result is 3 nested loops. If you, this is by looking at the loops, the other way of computing the complexity is very simple. If you kind of mathematically speaking, so how many elements are there in the product matrix? There are n square elements in the product matrix. And in order to compute each element in the product matrix, you take a row here and you take a column here and you compute the dot product. In order to compute the dot product, so you have to do n multiplications and n additions, or n minus 1 additions rather, or n additions. So if you think about it, so in order to compute each element, you have to do n amount of work, and there are n square elements in the product matrix. So the total amount of work is proportional to n cube. Are you with me on this argument? So n square elements. Okay, so you have to compute n square elements. So n square elements in the product matrix. Okay, so yeah, this is, and in order to compute each element, we do a dot product computation. So we take this row and we compute, we take this column, we take the dot product, and it takes n time. So each element, n amount of work. So overall work is n cube. So that's all. All right, good. So now let's go to the next program. And then after that, yeah, it looks like I may overshoot today also by some time. So Pratyaksh has a question. Let me take that question. Yes, Pratyaksh, go ahead.
Yes, sir. I still had that doubt about that n cube n power 4 time complexity thing. So I understand that there are 3 nested loops, and that should give n cube time complexity. Could you scroll down a bit, sir, please?
Okay, so do you understand, or is it do you need a
So
clarification?
if I can see the code, then I can tell you, sir. There you have
Okay, let's. You want me to show the code?
you've taken the index A IK. So yes, sir, where you performed the multiplication.
Oh, sorry, this is, I removed that open file.
So basically, sir, but you've taken two indexes from two different two-dimensional arrays and multiplied them. So will it still take the same time as taking one matrix? So
Sorry.
as in getting the value from one matrix. What I mean to say is here you're taking in that sum plus equal to statement, sir. You were accessing memory from two different arrays. So will it still be the same as one instruction? Wouldn't that make it n power 4 because this should be two
N power
instructions?
4. Why?
I mean, sir, I don't understand. If we're taking indexes from two separate matrices like that, shouldn't that increase the time complexity?
Mm, not sure. Let me increase the volume. So, uh, what I, so let's look at this again. So let's see if I can help you. How many times the statement on line 33 will be executed? It is n
N square
square.
times
How many times the statement on line 35 is executed? N cube
n
times.
cube, yes, sir.
And the statement on 36 is executed again n square times.
Yes, sir.
So the amount of work that you do to initialize sum is equal to 0. Let's say this is what we said. Let's say it is constant, some constant, okay, C1. And the amount of work that you do on line 35 is C2. There is no way n involved in it. You just do an array access. You do two memory, two read accesses from the memory. You perform a multiplication, you perform an addition, and you store it in sum. So you are performing four operations. We are calling
Oh,
all
okay,
these
sir.
four operations put together. Let's say that time is C2.
So that constant time that is taken to retrieve the array, we will not consider that in time complexity.
No, we say it is C2, but it is not dependent on n. If you just look at that statement,
Oh, okay,
it's
sir.
not dependent on the value capital N itself.
It's not dependent on the size of the whole
Yeah, it
matrix. That's
doesn't
why
depend on the
we are
size of
discarding
the
it.
array, that statement. So it just requires a constant amount of time to execute that statement. It doesn't dependent on.
Okay, thank you, sir.
And similarly, that here, if you see this also, it takes C3, and we said, so based on this, so we have C1 n square plus C2 n cube plus C3 n square. So there are some more questions. Let's see what these questions are. Ayush. Yes, Ayush, please go ahead.
Uh, Hello.
Yeah.
So I want to just confirm once more that when you initialize an entire array as A is equal to braces 0, is that's the exact same complexity as just doing it by a loop, right?
Yeah, that's true. That's true.
So is this just for the, so if I like initialize it as 1 comma 2 comma 3, is that also the same complexity as doing by a
Yeah,
loop?
that's true.
Okay, 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 fine then. Thank you.
Yeah. Shashwat?
So are array accesses considered uniform random access? Like,
Yes, yes. Yeah.
all right, thank you.
So I thought I will go through the bubble sort program today, but instead I will move it to the next lecture. And instead I will do something else. So now, so since you're all, we are kind of started looking at the time complexity of algorithms, I want to introduce some ideas here. So let's consider this. There's one problem. and you are so you take n amount of time. So let's compare different functions. So you have function n, and we want to compare n with different functions. So the first function is, let's say, so there is one problem which there is one algorithm which takes time, and there is another algorithm which takes n plus 1 time. So, so does it mean that the algorithm which takes n plus 1 time really bad when compared to n? So as you can see, one thing you can notice, like for example, let's say this is algorithm A naught, which takes n time, and this is algorithm AL. Let's no, let's not use AL. Let's say algorithm AC, some C, whatever. Algorithm AC, which takes n plus 1 time. So what happens is, if you compare these two algorithms, A naught and AC, so for different values of n, so like for example, if n is equal to 1, A naught does 1 amount of work, and AC does 2 units of work. When n is equal to 2, A naught does 2 units of work, and AC does 3 units of work. And if you take the ratio of these two things, like for example, the ratio, how fast is AC when compared with A naught. So initially it will be 2 divided by 1, and later on it will be 3 divided by 2, and after that it will be 4 divided by 3, and 5 divided by 4, 6 divided by 4. So as the value of n increases, so essentially we get something like n plus 1 by n. So, and if you compute limit as n tends to infinity, my infinity symbol is fantastically bad, sorry. Uh, so, yeah. So, this n plus 1 divided by n, so this is equal to 1. So, if you see that as n tends to infinity, so only for small inputs, like for example, only for n is equal to 1, 2, 3, or for very small inputs, you can see that you will see some performance difference between these two algorithms. But as n value increases, okay, so this is what is called as an asymptotic analysis. That is, what happens as the value of n increases, how these two algorithms behave. So not only n plus 1, it can be any constant n plus c. Even if it is any constant n plus c, you can see that so this limit, the ratio as n tends to infinity, when you take the ratio of these two, it turns out to be 1. So when you are working on when you have one algorithm which takes n time and another algorithm which takes n plus c time, you really don't need to worry about it so much. You can say, okay, whatever, it's all right. You don't need to sweat it out. But let's say you have another algorithm, so let's say which takes kn time. Okay, let's call it as the algorithm AK. And if you consider this, the ratio between this, okay, so the ratio between, so limit as n tends to infinity, you can take kn by n, this is equal to k. So the first algorithm, this algorithm AK gives a constant time speed up over n, and we are also kind of fine with it, because usually when there is a constant factor speed up, like for example, you may possibly buy a better processor and kind of take care of that, kill that constant or shave off that constant factor improvement you are seeing. So constants are also good. They are also fine. It's better, of course, we want to reduce that constant, but it's all right, because as the value of n increases, it is not the case that like it grows bad. But let's say, so you have another algorithm which takes time n square, then this is going to be an issue, because if you take limit as n tends to infinity, n square divided by n, this is equal to n. So what happens is the gap between these algorithms keeps increasing as the value of n keeps going. So in general, if you have a polynomial, so if you have an algorithm which takes n power k time, uh, and if you take the limit of it, so limit as n tends to, so limit as n tends to infinity, n power k by n, so this is n power k minus 1. So this is a problematic case. So in practice, what happens is, if you think about it, so when we are in this case, we don't even care, we don't even bother. But when we are in this case, in the second case where the improvement is a kind of constant factor improvement, we can kind of do few things the way we are programming things to see that the value of that constant k goes down, but we are kind of still all right with it. But when the algorithm, the complexity of the algorithm becomes n square or n power k, then as the value of n increases, the gap keeps growing substantially large. So these are problematic cases. So this is a problematic case and this is a problematic case. So when we study algorithms, when we study data structures, we want to design algorithms which are as close to n as possible. The reason is, anyway you are spending n amount of time to read the input, so you cannot, so that's all right. So if you have a linear time algorithm, you are kind of all right, because anyway n amount of work you are doing to read the input. But on the contrary, if you have n square algorithm, you want to see if you can try to come up with an algorithm which is, instead of n square, something like n log n or n power 1.2 and something like that. Okay. So if you have an algorithm such as these, you may want to shoot for algorithms such as whose time complexity looks like n power 1 plus epsilon or n power n times log n, something like that. So there is one more idea here I would like you to appreciate before before I show something else. Is like, for example, there is one algorithm. So in the matrix multiplication loop, we have considered, it's something like this. So C1, there is one step which requires C1 n square time, and there is another step which requires C2 n cube time, and there is another step which requires C3 n square. Okay. And what we are saying is, so it's okay, it's roughly, we can say that this whole thing, we can approximate it as n cube, because n cube is the dominant time, is the dominant factor in it. So because what happens is, if you take the proportion, if you take, like, for example, why is this a good approximation? So this is a good approximation because if you take C1 n square, C2 n cube plus C3 n square divided by n cube, this is the actual time, this is an approximation. And if you do limit as n tends to infinity, so what you get is C2. Because this term gets knocked out, it becomes 0. This term gets knocked out, and what remains is only the middle term, and it will be what you get is a constant. So that means this n cube is a constant factor approximation to this whole work function. So n cube is a constant factor approximation to the whole complex function. So that means once we say n cube, we get some intuition about how good that algorithm is. But instead, if you kind of say C1 n square plus C2 n cube plus C3 n square, then you get lost in these constants and you may not make much sense out of it. Well, in practice, when you get into the details, they may matter. But when we see at a high level, when you say the algorithm's complexity is n cube, or the amount of time that is involved is proportional to n cube, then immediately you will get a sense about the algorithm. Hey, you know what, this algorithm takes n cube time, maybe I should work so that instead of going for an n cube time algorithm, I can come up with a n square time algorithm. So this taking this dominant term is in this polynomial, so it is a good approximation. It's a good constant factor approximation. So and that's what we do in practice. And one more thing also I would like to say. So here you from the program, you know, like this is one step, this is another step, this is another step, this is step one. No, this is not. Yeah. So this is step three. Among these three, so the work two is the dominant thing. So similarly here, if you take a big program, so in big program, there is one part, there is, let's say, there is part one, part two, like that, there are 10 parts in your program. So one part could be reading the input, second part could be processing the input in some way, and part three could be processing, you know, the output produced by P2 in some other way, so on and so forth. And finally, part P10 could be some kind of concluding task. And let's say if P1 takes F1 of n time and P2 takes F2 of n time, and this takes F10 of n time. So the total amount of work done, you know, like it is F1 plus n plus F2 of n, so on and so forth. This is how we can sum up all these functions and say. But if you look at the whole of this thing, it kind of looks clumsy and you may not get a good sense of where we are spending a lot of time. So what we can do is, for example, you can take the dominant one. Like for example, this may take n time, this may take n square time, something else may take n cube time, something else may take again n square time, so on and so forth. Among all these functions, we can just take the dominant function, let's say n cube, and say the time complexity of this whole program is n cube. That is, it takes time proportional to n cube. And it is a good constant factor approximation. Good constant factor approximation. So why is this a good constant factor approximation? So if you see f of f1 of n, so on up to f10 of n, and let's say f4 is the dominant function, and if you take limit as n tends to infinity, and then if you compute this limit, if f4 is dominating f1, this gets knocked out, and f4 is dominating everything else except f4, everything else gets knocked out, and f4 kind of remains. So we say the function f4 is a good constant factor approximation for the whole time complexity of the program. I would like to see what's going on in the chat. How do we decide the denominator? So usually you don't, like for example, I'll answer that does P, so you look at different parts in the program. P1 is the first subpart in the program. Yeah, like think of that, like for example, in matrix multiplication, P1 is reading matrix A, P2 is reading matrix B, P3 is computing the product of the two matrices, and P4 is the printing the matrix on the screen. Are you with me on this discussion? How many of you are with me? For small values of n, we kind of, it's all right. We see as really we keep as the value of n keeps increasing, what can go wrong is what we try to understand. This is what is called as asymptotic analysis. So what we are doing is asymptotic analysis. That is, as the value of n increases, what happens? This is what we are. So now let's go back here and let me share my screen again. So in order to get some feel for this, so here we have a problem. Is we are plotting, let's say, let's plot different things. Okay, so in the first case, we are plotting t versus, let's call it as t plus 20. So here we are comparing, we are plotting. What we are trying to do here is, where is the annotation? Yeah. So here we are plotting n and n plus 20 and seeing how it looks like. So this is a Python program. So it's all right. If you don't understand, don't worry about it. Python free .py. Yeah. So you can see if it's a constant, like as the value of these curves will be parallel to each other as the value of n increases. But if you take the ratios, no, the ratio will become constant. That is, what is the speed up of the time of an algorithm which takes n plus 20 time versus n. Because again, I just want to say, so n plus 20 divided by n, limit as n tends to infinity, so it will be constant. So we are plotting n, and so this is n. So this curve is n. This curve is n plus 20. The gap between them is just it is constant. And like for example, so the age, let's say when you are born, so you could be 2 years old and your sibling is 1 year old, and you may think that you are really bigger than him and you can punch him up, or you can take care of him, whatever it is. But as years grows by, you see the difference between you is not really there. All right. So now let's look at a different graph and see. So now we want to plot a different graph, and instead of t plus 20, let's say you have t star 20. So now we are plotting two graphs. One is n, other is 2n. And like as the value of n increases, the difference between them, it keeps increasing. But if you take the ratio needs the same. Will be the same. That is 2n divided by n is 2. And let's plot it and see what happens. Okay, so you can see here. So this is n. This is 2n. So like for example here, if you see for n, this is 20, this is 20, but this is 40. But let's say this is 40 and this is this should be 80, I guess so. This should be 80, and the difference between them, so this is here, it is 40, whereas the difference here between them is 20. So this difference keeps increasing. Yeah, so but if you take the ratio will be constant. So the more, so now let's look at one more example, couple of more examples, and then we will conclude today's lecture. So now let's see 2 star t square. So this is real bad. this is real bad because you can see, as you know, limit as n tends to infinity, n square by n, this is no n. So let's see how it looks like. Now you can see how this graph is going phenomenally. So this is n, this is n square. And in fact, you cannot see this n because n square is looking so bad. This looks like, like almost like a straight line. N looks like a constant because the graph, the y-axis is so packed, and in order to accommodate n square, the graph is drawn that way. In order to see this thing clearly, maybe let's. So I'm plotting till n is equal to 100. So let's see what we can. Why I'm not able to kill this? Great. So let's say I can just take n is equal to 10 and see what happens. Yeah, now you can see some kind of difference. But you can see even for n is equal to 10, how the n square function is just kind of skyrocketing, but whereas n is linear time is kind of lying low. Are you with me so far on these graphs? Why we are seeing these graphs? Because we want to get some feel for what is happening, and when we plot them, it becomes more clear. Huh. So finally, there is one thing that we talked about. I will show it example and then we will conclude. That is, let's say if there is an, like for example, in the case of matrix multiplication, let's say the actual time complexity kind of if you do, no, like 2 steps require n square, so let it be 2n square plus, and 1 step requires n cube. So this is one kind of approximation for the matrix multiplication. And we say n cube is the dominant term. So we can approximate this whole thing as n cube time complexity. So what we can do is we can try to plot these two and see what happens. So the first plot is we have 2 star t star t plus t star. This is one. And the second plot is this. Okay, so here just want to say, so what we are doing here is this is nothing but 2n square plus n cube, and this is okay, one extra t needs to be added. This is n cube. So if we plot these things, how bad our approximation looks like, we will get an idea. Because we are saying this n cube is a good approximation for this. So we want to see how bad this n cube approximation to this whole thing. So let's, yeah. So now you can see that our n cube approximation is really that not bad because it is trying to catch up with that 2n cube plus, sorry, this is not 2n cube, this is 2n square. Yeah, this is, sorry. So this is 2n square. Yeah, this is 2n square plus n cube, 2 star t. Yeah, so this is good. So now you can go back and see, like this is not a bad approximation at all. This is n cube curve. This is n cube curve. And this is 2. Again, I did mistake there. I think I'm in a hurry to go maybe today. It's making many mistakes. 2n square plus n cube. And here, let me come back here. 2n square. I like 3. So are you with me here, at least till this point? So clear all my drawings. Let's go back here. So there is this question, instead of 100, can we go to 1000 and see what happens? This is, I just used it. Let's plot this graph again for any goes till 100 and see what happens. All right. Are you with me? Are you happy now that y n cube is probably a good approximation for what we have? And let's make it 1000 and see what happens. All right, so this is what we are trying to get through this plotting is we are trying to get this intuition on why this n cube is a good approximation. We just take the dominant term and use it as an approximation because the other small characters, they disappear as the value of n increases. So I think I have all this for today. So we will pick up this thread in the next class. And so maybe I will take some questions to continue this discussion in the next class, because I would presume that some of you may not be happy. So I will take, let's say in the next class, I will spend some 15-20 minutes revisiting these ideas and help you clarify these doubts, and then proceed further. So if some of you are lost, please, it's all right. Please review these ideas, think, discuss with your friends, try to get some clarity, make a list of questions. You can mail those questions to me or ask me on the Monday class. I will clarify them. So don't get tensed up. We will we'll make it clear. Okay. And yeah, so I think that's all I have for today. Thank you all. I think I enjoyed today's lecture myself. So I don't know about you. So, okay, bye guys.